So far, we have actually defined classical propositional logical consequence, right? So we gave the language, we gave the semantics, and the definition of logical consequence. Now, at some point, it might not be obvious what a given statement of logical consequence holds, right? So we would like to have not just the definition of logical consequence, but some means to decide in a given, for a given statement of logical consequence whether it holds, right? And this is what we are going to present now. So we are going to present a proof theory called tableaux, right? So basically, the idea behind tableaux is that you've got a set of rules, right? You've got some sentences, gamma sub 1 to gamma sub n, right? And you've got some set of rules to chop that sentences and start constructing a tree, right? A tree is a mathematical structure, right? We don't fuse too much about the definition, but it's something that starts from an initial list, and at some point it might open a branch, or it might not open a branch, right? It's a particular ordering. So we've got a set of rules to chop the initial list of sentences, and the tree, once we have chopped all the sentences, the tree will tell us whether this initial list of sentences is or is not satisfiable, right? So as we shall see later, the rules, so the tree is like a systematic search for an interpretation satisfying this initial set of sentences, right? Now, you might wonder now, well, I don't care about satisfiability, I care about logical consequence. Okay, that's right, that's a good point. But the thing is that you can, in classical logic, you can always translate any question about logical consequence into a question about satisfiability. And this is the trick we are going to use, right? Just to remind you, delta is a consequence of gamma, just in case there is no interpretation where all the gammas take value 1 and all the deltas take value 0, right? Now, delta takes value 0 in an interpretation, and this is part of the meaning of negation, just in case, if and only if, the negation of delta takes value 1, right? And this is the definition of an unsatisfiable set, right? So delta is a logical consequence of gamma, just in case there is no interpretation where all the gammas take value 1 and all the deltas take value 0, but this is equivalent to there is no interpretation where all the gammas take value 1 and the negation of the deltas take value 1, right? Which is another way to say this. This set is unsatisfiable. Just to recap, right? Delta is a logical consequence of gamma, just in case the set containing all the gammas plus the negation of the deltas, right? This is the union symbol in set theory. The gammas plus the negation of the deltas is unsatisfiable, right? So suppose now that someone asks you, well, is delta a logical consequence of gamma? How can we use tableaux to answer this question? Well, that's easy. You've got just to write as your initial list all the gammas and the negation of the deltas, right? Right? And then apply the rules that we are going to explain in a minute. So we said in the previous video that the tableau method is a way to check whether a given set is satisfiable. Given this connection between logical consequence and satisfiability, all we need to check to know whether delta is a logical consequence of gamma is to check whether this set, the gamma plus the negation of the deltas, is or not satisfiable, right? Okay, so our tree will start with a list of formulas, right? We have to place the gammas in the first place and then the negation of the deltas in the second place, right? And the three rules in order to extend the tree are like a systematic way to search for an interpretation making through all the formulas in this initial list, right? So the three rules can be read from the truth conditions of each logical connected, right? So for example, suppose that we've got a formula of the form A conjunction B in the tree, right? In order to analyze this formula, we have to extend the tree with two new formulas in the same branch, right, A and B. Why? Because there is just one case in which A conjunction B is true, namely the case where both A and B are true, right? That's why we don't have to consider just, we have to put both formulas in the same branch, right? Because there is just one case in which a formula of the form A conjunction B is true, right? Now, a different case is that of the negation of a conjunction, right? So, a conjunction is false in three cases, right? When either one of the conjuncts is false, when the other is false, or when both are false, right? So there are three cases where the negation of a conjunction is true, right? The case where one of the conjuncts is false, and the case where the other conjunct is false, and the case where both are false, right? So our tree rule will have to cover all the possibilities, right? That's why when we've got the negation of a conjunction, our tree will open a branch, right? So we will consider in a separate way what happens when one of the conjuncts is false, and that's why we write negation of A, and we will consider what happens when the other one is false, right? In this way, we make sure that we search for all the possibilities, right? All the other three rules work in a similar way, right? So we will say that a branch of the tree is closed whenever it contains a formula and its negation, right? When a branch closes, the tree is telling us that this attempt to find an interpretation doesn't work, right? Now, a tree closes whenever all its branches are closed, right? If the tree closes, then this means that the initial set of formulas is not satisfiable, right? Now, it might happen that some branches close, some others don't, but you have applied all the rules to the formulas that appear in the tree, right? So there is nothing left to chop, right? Or nothing left to analyze. In that case, the tree is open and it's telling us that there is an interpretation satisfying the initial set of formulas. So in order to make these things more clear, more precise, we're going to make an example right now.